First service announcement, again, this is not Ken's talk on ESAPI. He couldn't attend the conference. So I'm standing in and instead presenting work that I've done on object capabilities and how they can be used to enforce web and mashup isolation. So if you want, this is almost to some extent the right-hand side of the talk that is going on also in the other theater, where other people interested in object capabilities and in isolation from Google are talking about something related, even though the research efforts up to this moment were disjoint. So this is a joint work with John Mitchell and Ankur Tali in Stanford. So motivation, we are interested in the security of web mashups. This is a web mashup, it's their Google page. So by mashup, we mean that you download a page from one server, in this case Google, and it contains a lot of components, like the weather, a game, a YouTube page, all embedded inside the same page. Yes? You can't hear me? Okay. Fair enough. It was that way. I know. Okay, the better? All right. So the idea is mashups, we want to make them secure, okay? We have many components and we want to protect the web page that is embedding this component, in this case the Google page, from potentially malicious components. For example, the weather report turning into an attacker control page. And we want also to protect the components from each other. Okay, so the individual component may be compromised starting as a good guy and then due to an XSS attack or some other form of dynamic attack may be taken over by the attacker, or can be just in the first place provided by a malicious component provider. So we want to isolate this component in the browser. There are different approaches to do this. This morning, Philip gave a very nice and clear exposition of the client-side and server-side technologies in order to achieve that goal. In particular, on the client side, we could put components inside iframes and rely on the same origin policies, or we could use browser-embedded policies and other extensions or modification of the browser abstractions that could enforce isolation between these components. But that's a pretty coarse-grained way of separating them. And then there are other approaches, such as Facebook FBJS, Google Caja, and Yahoo's AppSecEU, that instead decide to put all these components in the same space in the browser, so it's logically in the same frame or iframe, but do some filtering and rewriting and wrapping at the server side. So they look at the code coming from the untrusted source and they decide whether to let it go through or whether to make some slight changes to the code so that once it's put in parallel with the other code in the browser, there will be no negative interaction. Our approach is to look at the server-side solutions, but build formal models for them based on programming language semantics, study the security properties of those models, and then validate the models against real applications. And in particular, we found ways of defining new enforcement mechanisms for Facebook and for AppSecEU, and found attack in the actual, at the time, current versions of these websites. So that's showing to some extent that it's good to complement the practical approach based on an intuition on which the programmer relies with a formal approach based on trying to prove a theorem on something that formally represents your mashup, and in that process you can find out either improved solutions or bugs. Okay, it's not the solution to everything, but it helps. So in this paper, in the paper on which this talk is based, there are a lot of theorems and a lot of rather complicated technical developments. Here I try to give you a more higher level intuition and just some definitions here and there when it's necessary in order to be concrete. So a basic mashup, as I will be talking about, is represented by this diagram where we have a trusted context, let's say the Google page, and a bunch of potentially untrusted components, the individual gadgets. We consider JavaScript as the language in which these gadgets are written. There are other options in the browser, but JavaScript is the most common one and is also the most fun for us to work with. And the results, though, that we actually have proven are language agnostic. So they could be transferred to other languages as soon as you give a precise specification in an operational semantic setting. But I'll stick to JavaScript for this talk. So each component, therefore, is just a term of JavaScript, a program or an expression, your favorite unit of JavaScript code. And a mashup in this setting is just a sequential composition of a bit of the different components written in JavaScript. Okay, so that means that we are not looking at the interaction between component 1 and component n and component 2, so they cannot send messages to each other. They are isolated. They may talk to the trusted context, perhaps, but they cannot directly interact with each other. So we can abstract that with a sequential composition. And the resource that we have to be careful about is the program heap. So in the case of JavaScript, is the memory where you're storing all your objects. So the mashup isolation problem in this setting is the problem of enforcing host isolation. So all those components should not tamper with the host, even if they may access certain useful functions. And they should not tamper with each other. Okay? So for each pair of indexes of components, component I should not tamper with the component J. So what we know so far is how to enforce host isolation. Okay, we have studied in detail JavaScript abstractions to enforce that, rewriting, filtering, wrapping mechanisms. They are published and they are relatively consistent with what is actually used in FPJS or in AppSecEU. But what we found that is pretty difficult to do intercomponent isolation, even using those techniques. So in particular, there are these library functions, that is, functions provided by the host that may provide the covered channels of interaction between components. And we need to be able somehow to, therefore, separate the privilege that each component has. So we looked at the capability-safe languages because that's a setting where there are very nice abstractions and programming paradigms to talk explicitly about privilege and controlling the propagation of this privilege. So in particular, object capability languages are using these ideas from general capabilities in the context of object orientation. Okay, we have the Joy language by Wagner, we have Reese's language and several others, and in particular also Miller, that is part of the Caja projects. So is both historically interesting, starting in '97, I believe, with Reese's thesis, up to right now, that is the next versions of iGoogle, including Google Caja, will be talking about object capabilities as well, and based on that. So it's important to build models also and formally analyze them. So these ideas seem relevant, but we want to write them black and white as definitions and study the property of definitions, stress them a bit, put them in exercise, and see whether they lead us to new insight. So in particular, now in the rest of the talk, I'm going to talk about what is our formal notion of capability system, that is of a language that can be classified as capability-oriented, and then define a notion of what it means to be capability-safe, and use that notion in order to enforce intercomponent isolation in the mashups. And then I will mention how we validated this approach on real examples. So the basic features of our capability systems, first of all, we have to define what the resources and the subjects of the system are. This is similar a bit to the ABC of access control. So the resources are the smallest possible things in a language that can be either read or written or executed. So in particularly in the JavaScript model, we focus on read-write permissions of memory locations. So essentially, we look in the heap whether one can read or write a location. And normally, these resources are organized as graphs. And so if a resource in memory contains a record, addressing other resources, then in the graph we will have edges going from the record to the other resources. The subjects are the pieces of a program that may manipulate resources, address them, and read or write them. And so a capability is a unique way, unforgeable, to denote a resource and the kind of access that can be performed upon it. So formally, in this simple setting, is simply a pair with the resource address and the permission, which may be read or write, but that can be generalized, and in particular, that P over there that represents the permissions could be extended to executable permission if we are accessing a function location or even more complicated policies. And what we needed in order to relate the language itself and these capabilities is a map that, given a term that represents therefore a subject, as I said before, tells us what are all the capabilities that the subject has access to, so therefore that it can eventually exercise. So the authority of a capability captures is essentially the transitive closure, if you want, of all the possible accesses that a process can do during execution, starting from the capability. So in this case, we have a capability up there in the tree pointing to the resource M1, but M1 contains pointers to other resources. Okay, so we're not just looking for this reachability of resources, we are a bit more fine-grained. So for example, the authority of this capability may be just that shaded area, because we look into the resources and we check for each resource contained whether there is a way to access it, but in a meaningful way in read or write, not just if it's stored there. Otherwise, we would include also M6 in this graph. So we need a more sophisticated analysis of these capabilities in order to define the authority. And authority will be what we care about, what authority a mashup component holds. So this concept of authority of a capability is easily extended to authority of a subject, because a subject is a piece of code. We look into the piece of code, and for all the capabilities that are in the piece of code, we collect their authority. So this is just a natural extension. Now, what's the idea? If we have capabilities implementing a mashup system, then we can reason about isolation by requiring that the authority of, for example, Alice and Bob, two different components, be disjoint. If we can make sure that this notion that is dynamic, depends on the execution of the programs, is disjoint, then we know that the two programs will not access the same resources. Okay. Now, note that we are in a sequential model of composition, but even if you were event-based before, you will call one of the two before the other. So we start, for example, in an initial state of the memory. We execute Alice code. We are in a new memory H2 denoted there. And now we could calculate, as I mentioned before, a notion of authority that is dependent on the state of the memory on the heap H. So we can, at the beginning of time, before running these mashups, we can check the authority of Alice in H1, but what we need to know in order to be safe is that the authority of Bob in H2 does not overlap. At that point, I know the accesses will not overlap. But that's not something easy to do. So we only have H1 before we decide whether this mashup is fine or not, before we put these components in, and so we must be able to decide on H1. And so we have to work a bit harder in order to get a condition on the initial heap. So what we'll try to do is define a notion of capability safety, and a check, essentially, that if the authority of Alice and Bob are disjoint in H1, then it will follow that they are disjoint also when H1 evolves to H2. So our definition of capability safety says that if we have a bunch of capabilities and two mappings, one telling me what are the capability of a term and the other what is the authority of a capability in a particular state, then all the accesses, that is all the read-write operation that actually appear in the trace of the program, must be included in the authority of the capabilities. That's condition 1.